Okay, in this lecture we're going to begin our Chapter 4 material on higher order linear differential equations. And in section 4.1 we'll start discussing the general theory of higher order, in general nth order, linear differential equations. And we're going to see throughout Chapter 4 that the theory and techniques for higher order linear differential equations is very similar to what we saw in Chapter 3 for second order linear equations. So let's start by considering our problem of interest throughout this chapter. Let us consider a differential equation of the following form, which involves y, y prime, y double prime, triple prime, and so on, up through the n minus first and the nth derivative of y. So here we have this linear combination of y and its first several derivatives, and it's equal to some g of t function. So, for instance, in Chapter 2, when we were looking at first order equations, we usually paired them with an initial condition. And in Chapter 3, when we were working with second order equations, we had a set of two initial conditions, y of 0 and y prime of 0. So for an nth order equation, we will usually pair this with a set of n initial conditions. We have the initial value of y at some time t naught, the initial value of the first derivative at time t naught, the initial value of the second derivative at that time, and so on, up through the initial value of the n minus first derivative at time t naught. And our question would be whether a solution of this initial value problem exists. So is there a solution? And if we find a solution, is it the only one? That is, if a solution does exist, is that solution unique? So to answer that question, we have the following theorem, Theorem 4.1.1 from your textbook, which we call the existence and uniqueness theorem. And this is very similar to the existence and uniqueness theorem that we saw for first order or second order linear equations. So here, if we are considering the initial value problem involving this nth order linear differential equation with a set of n initial conditions, when are we guaranteed that a unique solution will exist? And the answer to that question is that we need continuity of our coefficient functions. So here, if the functions p1, p2 up through pn, so all these coefficient functions in front of y and its derivatives, and g, that is the function on the right-hand side, are all continuous on some open interval containing the initial value of t, which we're calling t naught, then there is exactly one solution of this initial value problem, and that solution exists throughout that interval of continuity. So very similar to the existence and uniqueness theorem that we saw for first order or second order linear equations. We need all of these coefficient functions to be continuous once the equation is written in standard form. So for our first example, making use of this theorem, we are asked to determine intervals in which solutions of this differential equation are sure to exist. Now, to make use of this theorem, the first thing I want to do is rewrite my equation in standard form. So here, in standard form, we could rewrite our equation as the fourth derivative of y plus e to the t over t times t minus 1, y double prime plus 4t squared over t times t minus 1 times y is equal to 0. So let's look at these coefficient functions that we have. The function in front of y is what we call Pn of t. So for a fourth order equation, we would be calling this P4. Then we didn't have any y prime term. And then moving to our y double prime term, we would call this P2 of t. There was no y triple prime term. And then our g of t function is 0. This is a homogeneous fourth order linear equation, since that right-hand side is 0. So we need all three of these functions to be continuous. So here we can say that our functions P2, P4, and g of t are continuous as long as t is not equal to 0 or 1. We can't have division by 0. So we have continuity on the intervals from -infinity to 0, or from 0 to 1, or from 1 to infinity. That is the entire real line except t equals 0 or 1. So we have intervals, these three intervals, in which solutions of this differential equation would be sure to exist. And if we were to pair this differential equation with some set of initial conditions, then we could determine which of these specific intervals our solution would exist in. So for instance, if we paired this with a set of initial conditions, say where y at time -2 was given, let's say call it 1, then our initial value of t would be -2, and so we would have our solution defined on the interval from -infinity to 0. That is the interval containing -2. Or if I were to pair this with a set of initial conditions where the value of my function and its derivatives were specified at, say, 0.4, then our initial value of t would be 0.4, and we would be looking at the interval from 0 to 1. Or similarly, if we had a set of initial conditions given at, say, time 3, then our initial value would be 3, and we would choose the interval from 1 to infinity as the interval where our solution would exist. So here our existence and uniqueness theorem very similar to what we saw in chapters 2 and 3. In short, we need continuity of our coefficient functions on some interval for a unique solution to exist. Now the next thing we'll talk about in this first section is how to construct the general solution of an nth order linear homogeneous equation. So let's consider the following. Suppose that y1, y2 up through yn are n solutions of the homogeneous equation shown here. Then the linear combination y, defined by c1 y1 plus c2 y2 and so on up through cn yn, is also a solution for any values of these constants, c1 through cn. So that is, if we find n solutions of my nth order homogeneous equation, a linear combination of those n solutions is also a solution. So this is what we call the superposition principle, which says that a linear combination of a set of solutions would also be a solution. So as with chapter 3, the next question becomes whether every solution could be expressed as a linear combination of these n solutions, or whether there may be other solutions of a different form. So as with our second order linear equations in chapter 3, the answer to that question can be determined from the Wronskian of our set of solutions. So let's define what we mean by the Wronskian for a higher order equation. Suppose that y1, y2 up through yn are solutions of the nth order homogeneous linear differential equation. Then we would say the Wronskian of these solutions would be the function w, which would depend on t, or w, which depend on the functions y1 through yn. And it's defined as the determinant of the n by n matrix whose first row is the functions y1, y2 up through yn. My second row would be the first derivative of those functions. My third row would be the second derivative of each of those functions, and so on, up through my nth row, which would be the n minus 1 derivative of each of those functions. So very similar to what we saw for the Wronskian for a set of two solutions of a second order equation. So let's look at an example of calculating a Wronskian for a higher order equation. Here we are asked to find the Wronskian of the functions y1, y2, and y3, which are given. So here our Wronskian, which will depend on y1, y2, and y3, which are functions of t, is the determinant of the 3 by 3 matrix, where my first row would be the functions y1, y2, and y3. Then my second row would be the derivatives of these functions. So my derivatives would be 1, negative sine t, and cosine t. And then my third row would be the second derivatives, or the derivative of what I had in my second row, which would give me 0, negative cosine t, negative sine t. So we can evaluate this determinant by making use of a cofactor expansion, similar to what you've seen in your Calculus 3 course or in your linear algebra course. So here, if we use a cofactor expansion down the first column, we have probably the easiest expansion since our first column contains a 0. And so here we would have our first entry in the first column, t, times the determinant of the 2 by 2 submatrix I get by deleting that row and column. So this would leave me with negative sine t, cosine t, minus cosine t, minus sine t. And then moving to the second entry in my first column, I would have a negative times that entry 1 times the determinant of the 2 by 2 submatrix I get by deleting that row and column, which would leave me with cosine t, sine t, negative cosine t, negative sine t. And then plus the last entry in that first column is 0. So we are left with t times the determinant of this first 2 by 2 matrix gives us sine squared t minus a negative, so plus cosine squared t. Then we have minus 1 times the determinant of that 2 by 2 matrix would be negative sine t cosine t minus a negative, so plus sine t cosine t. And so we see that these terms cancel, and from the first term we have t times the sum of sine and cosine squared of t would be 1. So we are left with t for this Wronskian. So what does the Wronskian tell us about a set of solutions? So just like we saw in chapter 3, the Wronskian will inform us about whether a set of solutions forms a fundamental set. That is, whether every solution is a linear combination of some set of solutions. So we have the following theorem, theorem 4.1.2 from your textbook, which says the following. If we consider the nth order homogeneous linear equation, if these functions p1, p2, up through pn are continuous on an open interval so that a solution is guaranteed to exist, and if the functions y1, y2, up through yn are solutions, and if the Wronskian of that set of solutions is non-zero for at least one point, that is, if the Wronskian is not always 0, then every solution of this differential equation can be written as y is equal to c1y1 plus c2y2 and so on up through cnyn. And in this case, we would say that y1 up to through yn form a fundamental set of solutions. So as with the Wronskian in chapter 3, the Wronskian of a set of functions for a higher order linear equation determines whether they form a fundamental set of solutions, which means that every solution of our equation could be written as a linear combination of that set of functions. So let's look at an example making use of this theorem. Here we are asked to show that the functions y1, y2, and y3 form a fundamental set of solutions of the equation xy triple prime minus y double prime is equal to 0. So the first thing that I need to show that this set of functions forms a fundamental set of solutions is to show that they actually are solutions of this equation. So let's take a look at our first function. If y1 is given by 1, then my first derivative, y1 prime, would be 0. y1 double prime would be 0. And y1 triple prime would be 0. And so if I substitute these expressions into my differential equation, I'm looking at x times y triple prime, which was 0, minus y double prime, which is 0, and that is indeed equal to 0. So y1 is a solution. Now moving to my second function, if y2 is equal to x, then my first derivative would be 1. My second derivative would be 0. and my third derivative would be 0. And so substituting into our differential equation, we have x times y triple prime, which was 0, minus y double prime, which was 0, and that is indeed equal to 0. It satisfies our equation. So y2 is also a solution. And then lastly, for y3, if y3 is x cubed, then our derivative would be 3x squared. The second derivative would be 6x. And the third derivative would be 6. And so substituting into the equation, we're looking at x times the third derivative, which was 6, minus the second derivative, which was 6x. So we have 6x minus 6x, which is indeed equal to 0. So y3 is also a solution. And the next question is whether these three solutions form a fundamental set. So to determine if they form a fundamental set, we need to look at the Wronskian. So here the Wronskian of this set of solutions, y1, y2, and y3, is given by w of y1, y2, and y3, which are functions of x. And we would have the determinant of the 3 by 3 matrix, where my first row would be the functions 1, x, and x cubed. My second row would be the derivatives, 0, 1, 3x squared. And my third row would be the second derivatives, or the derivative of my second row, which would be 0, 0, 6x. So here, taking our determinant by either using a cofactor expansion or we see that this is an upper triangular matrix. So from linear algebra, the determinant of such a matrix is the product of the diagonal entries, 1 times 1 times 6x. So we have a Wronskian of 6x, which is certainly not equal to 0. So we can say that our functions, y1, which was equal to 1, y2, which was x, and y3, which was x cubed, form a fundamental set of solutions. Okay. Now the last part of this section has to do with linear dependence or independence of functions. So let's start by defining linear dependence or independence of functions. So here we would say that the functions f1, f2, up through fn are linearly dependent on some interval if there exists constants k1, k2, up through kn, which are not all 0, such that the linear combination k1, f1 plus k2, f2, and so on up through kn, fn is equal to 0. Otherwise, we say that these functions are linearly independent. So essentially what linear dependence means is that there is some linear combination of these functions which is equal to 0. Or another way to think about that is that one of our functions could be written as a linear combination of the others. In that case, they are said to be linearly dependent. Otherwise, the functions are called linearly independent. So if the only way for that linear combination of functions to equal 0 is for all of the constants, k1, k2, up through kn to equal 0, then these are said to be linearly independent. So let's look at an example determining whether a set of functions is linearly independent or dependent, and then we'll see how that connects to the idea of a fundamental set of solutions. So here we are asked to determine whether this set of functions f1, f2, and f3 are linearly dependent or independent, and if they are linearly dependent, find a linear relation among them. So to test for linear dependence, we're going to take a linear combination of my functions. So let's say some constant k1 times f1, which was 2t minus 3, plus k2 times f2, which is 2t squared plus 1, plus k3 times f3, which is 3t squared plus t, and I'm going to set this equal to 0. And the question is whether these constants, k1, k2, and k3, all have to be 0, or whether there are non-zero values which work. So let's take a look at this. If we expand each of these terms by multiplying our constant through, we have a 2k1t minus 3k1 plus 2k2t squared plus k2 plus 3k3t squared plus k3 times t is equal to 0. And if we group like terms based on the power of t, let's see what we have. Let's start with the highest order terms, the t squared terms. So grouping our t squareds, we have 2k2 plus 3k3 t squared. Then grouping my t to the first power terms together, we are left with a 2k1 plus k3 times t. And then grouping the constant terms, we have a negative 3k1 plus k2. It's equal to 0. And the only way for this function to equal 0, no matter what our t values are, is for each of these coefficients to be 0. So we need the coefficient of t squared, which was 2k2 plus 3k3, to be 0. The coefficient of t, which was 2k1 plus k3, has to be 0. And the constant coefficient, negative 3k1 plus k2, has to be 0. And I want to solve this system for k1, k2, and k3. So looking at my second equation, I see I could solve for k3 in terms of k1. It would be negative 2 times k1. And from the third equation, I could solve for k2 in terms of k1. It's equal to 3 times k1. And so if I take those expressions and substitute into my first equation, I have 2 times k2, so that would be 6k1, plus 3 times k3, which would be negative 6k1, is equal to 0. And we see here that regardless of the value of k1, well, this first equation is always satisfied. So regardless of what I choose for k1, that first equation is always true. So we see here that k1 is a free variable in this system. I'm free to choose any value that I'd like. So here, if I'm able to find non-zero constants that make the sum of these functions equal to 0, these functions are linearly dependent. So I can say these functions are linearly dependent. And to find a linear relationship among them, well, let's make a choice for k1, k2, and k3. So a simple choice of k1 would be maybe to let it equal 1, which would give me 1 times my first function, plus k2. Now k2 was 3 times k1. So if we choose k1 to be 1, k2 would be 3. So we have plus 3f2. And then plus k3. So if k1 was 1, k3 would be negative 2 times f3 is equal to 0. So this would be a linear relation among those three functions. So here we find they are linearly dependent, and we have the following linear relation. Another way to think of this, again, would be that we could write one of my functions as a linear combination of the other two. So if I were to solve for f1, I see that f1 is some linear combination of f2 and f3, so these are linearly dependent. Now, this idea of linear dependence or independence is related to the idea of a fundamental set of solutions. In fact, the Wronskian will tell us whether or not a set of functions is linearly independent or not. So let's take a look at this here. As a note, I will mention that the Wronskian can be used to determine if a set of functions is linearly dependent or independent. So let's take a look at that last example again, but making use of a Wronskian to see whether these functions are linearly independent or dependent. So again, the functions we were looking at were f1, which was 2t minus 3, f2, which was 2t squared plus 1, and f3, which is 3t squared plus t. So if I look at the Wronskian of this set of functions, f1, f2, and f3, which are functions of t, I would be looking at the determinant of the 3 by 3 matrix, whose first row would be 2t minus 3, 2t squared plus 1, and 3t squared plus t. Then my second row would be my derivatives, so 2, 4t, and 6t plus 1. And then my third row would be the second derivatives, or the derivative of the second row, which would give me 0, 4, and 6. So let's evaluate this determinant. If we use a cofactor expansion down the first column, we have our 2t minus 3 times the determinant of 4t, 6t plus 1, 4, 6, minus 2 times the determinant of 2t squared plus 1, 3t squared plus t, 4, 6, plus the last entry in my first column, which is 0. So looking at this, we have a 2t minus 3 times, taking the determinant of this 2 by 2 matrix, we have 24t minus 24t plus 4, so subtracting that quantity, minus 4. And then our minus 2 times the determinant of this 2 by 2 matrix gives us 12t squared plus 6 minus 12t squared plus 4t. So subtracting that quantity, a minus 4t. And then simplifying a bit, we see, well, our plus minus 24t cancel, and the plus minus 12t squared cancel. So expanding what we're left with, we have a negative 8t plus 12, and then a minus 12 plus 8t. And summing these terms, we're left with 0. So if our Wronskian is 0, then our functions are linearly dependent. If my Wronskian of a set of functions is non-zero, then our functions would be linearly independent, and they would form a fundamental set of solutions. So we say that a set of solutions is a fundamental set if the functions are linearly independent. That is, if the Wronskian is not always 0.